Hi, can you hear us?
Yeah, I can now.
Okay, very good. No, we were wondering whether Luis and Yaroslav has uploaded the slides or not, because we cannot see the slides.
I think in my email I have something from Yaroslav and also from Luis, but I did not know that I should upload them. Let me check that while
Hello,
Luis is connected.
yeah,
Okay.
I'm connected. I haven't uploaded the slides, but I can try to do it now.
Okay, I mean, doesn't matter. You can show it if you want and then upload, but it's better if you upload it right now so that the people can read them, even if they are not following this session due to the time zone.
That's right. Let me try to do it now.
Okay, and also Yaroslav, I think, no. But
I will check. As I say, I think I have something in my email, but I will check with him.
Okay, yeah, because I cannot see him connected yet.
That's true. He is expecting to speak, and I have a draft, so maybe he should upload the final, but it's okay.
Okay. Anyway, he's not the first speaker, so it's fine.
So welcome everybody. This will be the end with a NuStorm session. Okay, sorry, we start with the recording in a while. Okay, welcome to this joint Innovate NuStorm session. So we have a presentation on individual aspects of both projects and also an attempt to show possible synergies between the two groups. So the first speaker is Fabio Pupilli from INFN Padova. He will talk about aspects of lepton reconstruction in the instrumented decay tunnel and possible detectors for the cross-section program. So Fabio.
Okay, can you hear me?
Yes, maybe try a bit louder.
Yes, it's better now?
Yes, a bit better.
Okay, so I will also try to share the screen if it's needed. Okay.
Yes, we can see it.
Okay, good.
Fine.
Okay. So as Andrea was saying, my talk will be divided essentially into parts. The first one, I will recap the strategies for the charger lepton reconstruction in the Nufact tagger in order to monitor the neutrino flux. While in the second, I will provide a not exhaustive, but mostly qualitative overview of the possible concept for detectors that can be used in the high precision cross-section program. So just a recap of the Nufact idea. The idea is to bypass the main systematics that comes with the estimation of the neutrino flux that are related essentially on the hadron production and to the beamline geometry focusing in order to provide the neutrino flux with a precision of 1%. And this is done by the concept of monitoring neutrino beams in which the measurement of the rate of leptons, of charged leptons, is used as a proxy to monitor the neutrino flux. In this way, we plan to measure muons and positrons, large angle muons and positrons in the instrumented decay tunnel to monitor the muon neutrinos and the electron neutrinos respectively coming from the kaon decays, while we imagine to measure muons, low angle muons in the forward region in order to monitor neutrinos coming from the pion decays. For a complete overview of the project, I remind you that there has been a talk by Giulia Brunetti a couple of days ago, and I invite you to have a look. This is the sketch of the Nufact beamline in the static focusing option, in which the focusing of the mesons is achieved by a quadruple triplet just in front of the target, and it is coupled to a slow proton extraction. And for the results that I will show you in the next slides, I will assume a 2-second long extraction with 4.5 times to the 13 proton on targets. This beamline is optimized for the transport of mesons with a momentum of 8.5 GB and with a narrow momentum width of 10%. And as you can imagine, the name of the game is to have a large meson yield, that means a larger neutrino flux, while still having a sustainable background on the tunnel walls to not blind the detectors. We are still pursuing also the horn-based approach, and you will find further details on the next one of the next talks by Michelangelo Pari in this session. Concerning the detectors, you will find more details on the next talk by Fabio Jacob, but I would like just to remind you the concept of the instrumented decay tunnel that is based on a sampling calorimeter with a longitudinal, radial, and transverse segmentation, and it is based on small units called lateral compact modules. And this is used for the separation of the signal, the position signal for the other charged backgrounds, while for the suppression of the gamma background coming from pi 0 and also from electromagnetic interactions in the beamline, we use these yellow rings of scintillator tiles that you can see in this sketch, and that we call T0 layer. And by exploiting them together with the calorimeter, we can differentiate the different topologies. In these plots, you can see the heat rate on the tunnel instrumentation as a function of their position in the Z coordinate for the different components of the instrumentation. So in the top left, there is the T0 layer, while the other plots refers to the different layers of the calorimeters. And you can see that the maximum rate amounts to is of the order of the megahertz, with the main backgrounds coming from uncollimated pions, the green component, halo muons, that is the blue one, and other kaon decay modes, that is the yellow one, that is start to contribute at a higher Z. Of course, the halo muons are the main background for the monitoring of the muons coming from the kaon decays, while the positron background, even if it's not that big, that is not that large, it still represents a not negligible background for the positron identification, since the particle species actually is exactly the same as the signal that we are looking for. And as you can see, for example, in the top right plot, it is more or less at the same level as the signal that is the golden component in this histogram. So coming now to the algorithm for the lepton identification. In order to set them up, we developed a full jump-force simulation of the detector that has a neat level detector response, and that it is being validated with the prototype test done in the past years at CERN. The analysis chain foresees two steps. The first one is the event building, that starts from the selection of an event seed, that is an LCM with an energy deposition greater than 28 eV, and that actually is intended in order to preselect already electromagnetic showers. Then it's compatible in space and time in the other layers of the calorimeter are associated to the seed in order to construct events, and the procedure is iterated for all the recorded bits. As you can see in this bottom left plot that reports the Z coordinate of the reconstructed events at the event builder level, there is already an enhancement of the signal that is the golden part of this histogram, with a suppression of the MIP-like part, the MIP-like signal that is the blue one for the halo muons. The final separation of the signal from the other backgrounds, both charged and neutral, is done by a multivariate analysis based on a neural network that uses 19 variables, exploiting the energy pattern in the calorimeter, the event topology, and also in a transparent way, the information coming from the photon veto. So in this way, we are able to achieve an efficiency of 22% in the selection of positrons from K3, with a signal-to-noise ratio of 2, and therefore these efficiencies comes from the geometrical acceptance of the target. This variable, the longitudinal position on the tunnel, is one of the variables used in the fitting procedure to constrain the neutrino flux that will be explained in the talk by Antonio Branca later in this workshop. In order to have a fully realistic treatment of the pile-up effects, we also set up a software framework that is able to simulate the target response at the single channel level. It starts from the conversion of the energy deposition coming from the jump-force simulation in photoelectrons, and this conversion is driven by test beam data. Then the response of the silicon photomultipliers that are used for the signal readout is simulated using the gossip software that allows for a control of many parameters of the sensor itself and of the electronics associated. The waveform is digitized, the waveform of each single channel is digitized, and a path detection algorithm is used to process this waveform and to reconstruct the peak amplitude and the time of the peak itself. These information are then used for the standard reconstruction chain that I explained before, and this is used for the final identification of the leptons. So as you can see in the bottom left plot, I reported here the efficiency as a function of the signal to noise ratio for different values of the neural network classifier. And the green line refers to the waveform simulation approach, the one that I described here, while the red one is the standard analysis that I reported in the previous slide. And you can see that there is already a very good agreement among the two. The difference is quite reduced. And we expect also to close this gap by processing the neural network training sample with the same chain that is not done up to now. But the message here is that there is a full control on the pile-up effects and on the reconstruction chain just up to the signal processing level. Coming now to the reconstructions of muons, the large angle muons coming from the kaon decays are reconstructed with a analysis chain that is actually similar to the one of positrons. So it starts with an event building, but in this case, the event seed is selected in order to already pre-select MIP-like particles. And indeed, you can see in the bottom left plot that already at the building level, again, here is reported the distribution of the events as a function of the longitudinal position of the tunnel. Already at the building level, we have a suppression of the background, the electromagnetic-like backgrounds, and the main background comes essentially from halo muons. Then the final selection of the signal is performed again using a neural network that exploits 13 variables that encodes the track topology to suppress the halo muons and also the energy pattern to suppress also the other source of backgrounds. In this case, the efficiency amounts to about 34% with a signal to noise ratio of 6 that is greater with respect to the previous case, also because of the 12 times larger branching ratio of the K muons with respect to the K3 decay. Coming now to the muons from the pions, since they are low angles, they cannot be measured in the tagger because they are out of the tagger acceptance itself. So we are thinking about instrumenting the region after the hadron dump with the muon stations interleaved with absorbers. This is a sketch of a preliminary configuration in which there are 8 muon stations. And the idea is to exploit the correlation between a number of transversal stations that gives actually the muon energy by range and the neutrino energy. And the difference in the distribution can be used to disentangle the contribution from signal and halo muons. The detector technology for this type of approach is still to be assessed, but the important point is that the maximum muon rate in the static focusing approach with a slow extraction of protons amounts to about 2 megahertz per square centimeter. That is not impossible. That could allow an event-by-event monitoring of this type of muons. Coming now to the spectra that we expect in the enabled configuration that is being studied up to now. These spectra are calculated assuming a 500-ton liquid argon neutrino detector with a cross-section of 6 by 6 square meters placed at 50 meters from the hadron dump. And there is also the assumption to have 4.5 times 10 to the 19 proton per year. And with these assumptions, we expect to have about 10,000 Churchill current interactions in about 2 years of data taking, with a spectrum that is peaked at about 4 GB. So it's optimized for the Dune cases. And the red part of the histogram in this plot represent the neutrino comings that are produced in the tunnel, so that are directly taggable by the monitoring of the muons, and they represent the 80% of the whole amount. For what concerns the muon neutrinos, we expect to have in about 2 years about 1 million charge current interactions. And the low energy parts coming from PINE will be monitored through the instrumentation of the hadron damped region, while the higher energy part from kaons is monitored thanks to the measuring of the muons in the hadron damp in the Tagger, and will be also used to further constrain the electron neutrino component. A plus for what concerns the muon neutrino is the fact that we can provide on an event by event basis also the neutrino energy, and this is done with what we call the narrow band of Fluxes technique that exploits the strong correlation between the energy of the neutrino and the radial position of the interaction vertex of the detector. This can be done thanks to the narrow momentum width of the beam and the finite dimension of the near detector that is placed at a small distance. And by selecting interactions in small radial windows, in these plots, they are selected in windows of ± 10 centimeters in different colors, with the lower frequency referring to larger radius in this color scale. And by selecting these different components, and by using the width of the pion peaks that can be differentiated from the kaons one by a rough energy cut, we can give an estimation of the energy resolution that can be achieved, and it ranges from 8 to 25% in the dune energy range, for which NUBET is actually now being optimized. Coming now to the cross section, as you can imagine, and this is actually the goal of one of the main goals of NUBET, it is an ideal facility for the high precision cross section measurement at the GB scale. If we take into account the relation that among the observed events in the cross section, we have an excellent control of the first term, the flux at the level of 1%, thanks to the monitoring of the leptons. We can also provide the energy a priori of the neutrino with a precision of 20–20%, and it's very important for the differential cross-section measurement, and also to remove biases that comes from nuclear effects and final state interaction that are affecting the usual energy reconstruction that is done through the final state particle kinematics. Finally, the other terms, and this brings me to the last part of my talk, is the one that contains the efficiency and the cross-section. So to measure the convolution of these two terms for the oscillation program, we can imagine to use replica detector technologies as the ones employed in the next projects like Dune and HyperK. But in order to decouple the cross-section from the efficiency, we need also complementary high efficiency detectors that are able to study in greater details the interaction. So the message is that actually a complex with a variety of detector concepts is highly desirable, starting from, of course, water Cherenkov and liquid TPC approaches in order to cover both the projects. But they should be complemented with fine-grained detectors with superior particularity performance and low thresholds that could allow for a complete characterization of the hydraulic system. It's really important for the model building. This in any case it's just a part of the game, because it will be also very important, pivotal in some sense, also for the model building, also to have detectors with hydrogen and deuterium targets that are not affected by nuclear effects, and that could provide a solid basis to build models that can be scaled to higher Z materials. Most of the ideas in this slide, and also in the next one, are reported in this recent work that we recently published with some collaborators of NUBET, with Marco Martini, and that you can find at this link. And coming now to the Dune case, so it's not a secret that ProtoDune, both single phase and dual phase, could be an excellent option for the measurement of the convolution of the cross-section and the efficiency for the Dune case. This is because they have the very same technology as the Dune fire detectors, and especially for the ProtoDune single phase, its response has been already fully characterized in a test beam exposure to charged particles, and it allows for an almost full containment of the neutrino interactions, unlike the liquid argon near detector of Dune that it needs to be segmented in smaller TPCs in order to sustain the higher neutrino interaction rate at the near location of Dune. So the simultaneous use of a liquid argon and a gas phase argon TPC could be an ideal solution to decouple, as I said before, the neutrino cross-section in argon from detector efficiency. An example in this case is provided by the TPC of the near detector of Dune, that is actually inherited from the ARIS-1, but is operated at 10 times its pressure and has an active volume of 1.8 tons. So the main advantages of this approach is that, of course, it has an excellent momentum resolution given by the measurement in the magnetic field, but also it has an improved particle identification and a significantly lower energy threshold that comes from the lower density of the material. And this could allow for a full characterization of the atomic system that I said that is very important. As an example, here is reported the plot concerning the efficiency on the reconstruction of protons as a function of the proton kinetic energy, and the threshold is of about 20 MeV as reported in the Dune near detector CDR, and they expect to push it down up to 5 MeV with exploiting machine learning techniques. For the Hyper-K case, there is an intriguing opportunity that is represented by the exposure of a small water Cherenkov detector that is the water Cherenkov test experiment. It is planned in the next couple of years. It is actually small, it's of about 50 ton mass, and it has an height of 4 meters with a radius of 4.1 meters. As I said, it represents an interesting opportunity because, as in the case of ProtoDune, it will be already fully characterized with an exposure to charged particles in test beam. Despite the fact that there is a smaller size of the photomultipliers, and this is driven by the fact that the Cherenkov bricks will have a smaller size in this smaller size detector. Actually, the detector technology and the event reconstruction are very similar to those of Hyper-K. So this means that there will be the same cross-section times efficiency convolution for both the detectors, more or less. And given the small mass, actually, it's not possible to have enough neutrino interaction with a moderate intensity beam like NU, but it will still be possible to measure double differential cross-section exploiting the mu neutrino. Again, as in the case of the liquid argon case, fine-grained detectors with water targets can be used to disentangle the neutrino cross-section from the detector efficiency. Here I report 2 examples of this type of detectors. The Wagashi one that is being used currently as a part of the near detector suite of T2K, and is composed by a target of water of 0.6 tons. That are actually segmented in small cells of the order of some centimeter, enclosed by a 3D grid-like structure of plastic scintillator strips that allow for a 4-pi reconstruction of the products of the interaction in water. The setup is complemented by the baby mine spectrometer for the measurement of the muon momentum. Another approach is represented by the Ninja, that again is placed in the suite of near detectors of T2K, and it's based on nuclear emulsion films as sensing devices, and is complemented by scintillating fiber trackers that allow to timestamp and match the tracking emulsion. And what is important in both cases is the fact that again they can push down the threshold on the momentum for the hadrons for a full characterization of the hadronic system. For example, in Ninja, this threshold can be pushed down to 200 MeV for protons and 50 MeV for pions. Finally, as I was saying before, the measurement of neutrino interactions with hydrogen will provide a clean and solid base to build reliable models that are not affected by nuclear effects, and that can be scaled up to higher Z materials. Recently, indirect approaches have been proposed. They are based on the technique of the transverse momentum imbalance. This transverse momentum imbalance is actually induced by nuclear effects, and it can be used to disentangle hydrogen interaction from those with the other nuclei in composite materials, like, for example, hydrocarbon targets. As an example to explain the concept, I reported here this plot that is that refers to CCQE antineutrino interactions on protons in an hydrocarbon target. The process reports the cross-section as a function of the delta PT. And actually, since the lepton and the neutrons are produced back to back, if there are no nuclear effects, like in the case of the hydrogen, you expect at the generation level, so without smearing effects, a peak at 0 in this distribution, while for carbon interaction, you expect to have a smearing due to the nuclear effects. So despite these indirect approaches that for WAS the systematics are still to be fully assessed, a fully unbiased measurement will be provided, of course, by using a liquid hydrogen target. Actually, this is a challenging task in case because there are constraints that are posed by model safety requirements for underground labs. But there is a growing interest in this type of approach. And in particular, recently, there has been a letter of intent in the Normal framework that proposed to revive the time-honored magnetized bubble chamber technique, but that already provided a lot of data in the 70s and the 80s. For example, here there is the 50-foot bubble chamber used in Fermilab. But upgrading this type of technique with modern digital camera technology and machine-assisted reconstruction techniques in order to improve the precision of the reconstruction and also the data analysis speed. So this ends my quick overview, and I thank you for your attention.
Thank you, Fabio. So can we check if there are questions in Cagliari? Is there some raised hands there from the audience? It seems not. Okay, so thank you, Fabio. I think we can proceed then. The next talk will be by Luis Alvarez Russo, that will talk about the physics reach of Newstorm in terms of cross-section and exotic physics. So Luis, are you there?
Yeah, I'm here. I'm sharing the screen.
Yes, we can hear you well.
Great. Can you see the slides?
Yes, just use the...
Now it should come to
yes,
full screen.
Perfect. You can start.
Okay, thank you. So indeed, the decay of muons stored in a ring can be used to deliver a flux of neutrinos with an energy distribution and flavor composition fully determined from muon decay, and a normalization which can be determined with a precision of less than 1%. I'm going to leave the details on how such a Newstorm facility could be realized, in particular at CERN. We'll leave that to the expert in the forthcoming talks, and focus now on the physics program that can be achieved with such a precise beam, focused specifically on measurements, very precise measurements of neutrino cross sections, including possibly some exotic beyond standard model reaction mechanisms, and also detailed study of short baseline flavor transitions and sterile neutrino searches. So indeed, such a Newstorm facility is the ideal place to perform very detailed measurements of neutrino cross sections, including both elementary processes and neutrino nucleus scattering. And this is not only interesting by itself to provide information about the axial structure of hadrons and the nuclear response, but in particular, it is crucial to help achieving the precision goal of oscillation experiments. So in particular, these measurements can provide priceless input to develop better models, tune those models, and ultimately lead to more precise event generators. And I would like to stress that mismodeling in event generators can lead to systematic errors, even if those generators are tuned to the best available data. So here I mention elementary processes. By elementary processes, what I mean here is neutrino scatterings on nucleons, on protons and neutrons, which are poorly known process because the measurements that we have at our disposal are old, performing in old bubble chambers with poorly known fluxes, and any new information we could gather about these processes is priceless for the development of event generators. And as it was discussed in the previous talk, these elementary cross sections could be measured either directly on hydrogen or deuterium target, or indirectly using hydrogen enriched targets and kinematic subtraction technique. Then obviously placing an experiment like any of them in a Nusstorm beam has the added value that one can measure cross sections with electron and muon electron neutrinos and muon antineutrinos in very similar conditions, which also, given the precision, can also allow to explore relatively small effects like radiative cross sections or even non-standard interactions, who could reveal themselves in flavor differences. So, and here in this for this elementary process, we of course have in mind quasi-elastic scattering, which is fairly well known, except that the nucleon axial form factor is still not determined with enough precision. And if this is achieved, this process could be used as a standard candle to constrain neutrino fluxes in other experiments. But I have mostly in mind processes beyond quasi-elastic scattering in elastic processes, started from single pion production. We know that single pion production is dominated by the prominent and isolated delta resonance. But even in this case, the interference between resonance and non-resonance amplitudes play a role, and also unitarity corrections are very relevant, particularly as far as one starts to increase the invariant mass of the final hadronic system. And indeed, if we increase this invariant mass going above the delta peak, then we encountered a very complicated dynamics, including several overlapping resonances, which can interfere. We can have coupled channel effects. And of course, we also open the threshold for other inelastic processes, such as double pion production, eta production, or associated strangeness production. So for all these inelastic processes, we, thanks to isospin symmetry, we can obtain interaction about the vector part of the hadronic current from electromagnetic scattering, from using scattering with real photons or virtual photons, that is electron scattering, and this is great. And now in the axial sector, thanks to PCAC, we also can relate the axial current in the forward direction, so at q squared equal to 0, can be related to pion nucleon and in general meson nucleon scattering amplitudes. But we have almost no information about the behavior, the structure of this axial current at q squared different from 0. And of course, then now as we increase q squared and w, we enter the regime in which we should perform the transition from hadronic to quark degrees of freedom. So we go from the resonance region to the deep inelastic scattering regime. And this region, which is very relevant for Dune, is indeed poorly known. And for instance, we have open questions about what is the role that quark-hadron duality could play, or the role that once we move to deep inelastic scattering, the impact of higher twist corrections, and coming to exclusive channels, which is then we need to understand hadronization So these topics were covered in detail by the plenary talk by Jorge Morfin, I think, yes, on Tuesday. And what I would like to add to this is that with the setup that is currently under consideration for Newstorm, the fluxes that will be produced nicely overlap with the region in which all these processes can be studied. Of course, we also are interested in neutrino scattering on heavy nuclear target, in particular using different targets. And here, again, Newstorm can really have an impact by describing the difference between scattering with electron and mu neutrinos, which these differences are particularly important at low energy and low momentum transfers. As this is illustrated in this plot here, you can see here that indeed at for lower energies there are differences in the case of electron neutrinos and mu neutrinos, and those differences they result from a subtle interplays between kinematic factors and response functions. For example, if we take a fixed neutrino energy, look at the double differential cross section as predicted in this continuum RPA calculation, we can see that depending on the angle, the mu neutrino cross section can be higher than the electron neutrino one, or vice versa. Now, just dwelling more on this, so Newstorm would be in the position to really obtain very high statistic results for the cross-section ratio. So the ratio of electron neutrino to mu neutrino cross sections, and this is one of the largest uncertainty for dune electron appearance measurements. So, and this precise determination of this ratio would actually help achieving the required sensitivity to CP violation with a smaller exposure, and therefore using less resources at the dune experiment. Now, more specifically, with this kind of measurements on heavy targets, it is possible to achieve a better understanding of the initial state, particularly if different targets are accessible, study the role of correlations, and very importantly, study better the role of meson exchange currents. So meson exchange currents, we know that they are interactions of the external probe with pairs of nucleons. They are known to be important to describe the so-called deep region that is met between the quasi-elastic peak and the inelastic peak in the inclusive cross-section for electron scattering. So this the importance of this, the relevance of this kind of mechanism has been shown, and it has also been found that this kind of mechanisms are very important to reconcile mini-boom measurements with the what is known about quasi-elastic scattering from hydrogen and neutrino measurements by adding some extra strength. New and more precise measurements that allow to constrain better this mechanism would be important to help understand discrepancies with theory, or at least with the way theory has been implemented in event generators that have been found at Minerva. This can be seen here in this, again, double differential plots as a function of the available neutrino energy for slices of the transverse of the three momentum, and one can see that there is an excess of events compared to the prediction in this case with Gini, which is found more or less in the region where the two peaks, the quasi-elastic and elastic peaks, would overlap, corresponding to the region where the kinematic regions where meson exchange currents are important. Similar kind of excess has also been found by NOVA. Okay, then of course, again at higher Q square and invariant masses of the hadronic system, with nuclear targets, with different nuclear targets, it would be possible to understand better nuclear effects on the determination of parton distribution functions, and in particular, just address the differences in the nuclear effects that can be that can be there between weak and electromagnetic processes, that is in deep inelastic scattering with neutrinos or with electrons. And this would be very helpful to understand and clarifying the tensions that still exist between those two kinds of measurements, particularly at low Bjorken X. Again, this was also discussed in Jorge's plenary talk. So then, of course, it is important to look also at exclusive final states. This includes 1 and 2 nuclear knockout, single and multiple pion production, and also other mesons. And we know that that the composition and the distribution of these final states, when they are produced in nuclear targets, they have a large influence from final state interactions. This is illustrated in this plot produced with the Giesen-BUU transport model, where one can see that in this case, pion spectra on an iron target, they are largely distorted due to, first of all, the strong pion absorption in the delta region, and the fact that charge exchange can leads to sign feeding from the dominant, in this case, pi plus channel, to the smaller neutral pion channel. So again, better understanding of this kinematics and composition of this kind of final states is not only interesting, but also very relevant for calorimetric neutrino energy determination in oscillation experiments, upon which the oscillation analysis ultimately depend on. Now, in a Newstorm facility, given the precision that can be achieved, and provided that one has enough statistics, it's also possible to go after so-called, let's call them rare processes, which by this I mean here processes with smaller cross sections. This includes strangeness that I mentioned before, but also coherent meson production, trident scattering, leading to dimuon pairs, which is interesting in particular because they are possible beyond standard model contributions, given by, so in the case that they are, for example, lighter C prime mediators that would enhance the cross section with respect to the standard model prediction. And rare processes include also single photon emission in neutral current interactions, which is important as being one of the not so well constrained backgrounds that contributes to the electron-like signal at minimum. So this process is actually under investigation at Microboom. There was a report in the workshop. I think it was also on Tuesday, and it was shown that Microboom plans to reduce the upper limit obtained by T2K by a large amount. I think it was a large reduction in this way they will be able to start excluding, ruling out the possibility that the mini-Woon excess come from photon events, but they will still be very far away from the current standard model predictions for neutral current single photon emission cross-section. So we need some new experiments, and again, Nustorm could contribute to study this process, which is, among other things, is also a background for other alternative beyond standard model explanations that have been proposed to explain for the mini-Woon anomaly. So these exotic processes that have been proposed as explanations of the mini-Woon excess, they can be in general classified as heavy neutrino production in neutrino scattering processes. So the produced heavy neutrinos would decay to photons or directly to E+ pair, and therefore could be, in the case of mini-Woon, could be misidentified as coming from electron neutrinos. Detailed experimental studies of these processes would therefore require a detector that is capable to distinguishing between photons, electrons, positrons, and also E+ pairs. So those heavy neutrinos could be produced electromagnetically, so that is with a photon mediator bias on transition magnetic moment. They could be produced in neutral current interaction with the standard C boson mediator, or with some dark sector C prime mediator. On nuclear targets, this heavy neutrino productions could be coherent, or where the final state is where the nucleus remains in the ground state, or incoherent, where the nucleus, the target is excited to every possible final state. In general, at least in the case of mini-Woon, not including meson production. So now it can be actually seen that in the case of light mediators, which we take the extreme case of a photon mediator, the coherent process here, we can see in this cross-section plot, is given by the red line. These are calculations on carbon. So the coherent process dominates over the incoherent one. In the case of heavy mediator, as the standard model C boson, the situation is reversed. It is the incoherent cross-section that dominates. Now, what happens in the case of such a light mediator, like the photon, and in which then leads to the coherent process, is that coherent processes are very forward picked, and this creates a difficulty to explain the mini-Woon anomaly, because even if one can describe well the excess of events, the energy distribution of the excess of events, the angular distribution comes out too forward peaked. So all you can see here all the strength is accumulated in the first beam, which is not what is observed by mini-Woon. So this is the reason why, in general, more exotic models with C prime mediators can do a better job in reconciling both the energy and the angular distribution. And this here you can see an example of such a calculation using a 1.2 GeV C prime. In any case, so even if it is fair to say that all these kind of models they are not really very successful explaining the mini-Woon anomaly, it is nonetheless true that these mechanisms have some theoretical ground, and it would be worthwhile to learn more about them. Then let me mention in passing that also so that heavy neutrinos, not so heavy as in the previous case, but still heavy, could be also be produced in the case of muons and also of mesons. So this is illustrated here in this cartoon, and these heavy neutrinos could propagate and eventually decay in the detector. This, of course, could be also studied at a Newstorm facility, although in this case one would not be really using the excellent flux available from storm muons. So then finally, let me mention that Newstorm has a unique sensitivity to short baseline flavor transitions. And here the key aspect is that both muon neutrino appearance and muon anti-neutrino disappearance could be measured at the same time. In the case of muon appearance, one would have to observe negative muons in a large mu plus background, which requires a very good charge identification. And in the case of the disappearance channel, it would require to observe positive muons using spectral distortion, which for this accurate momentum measurement is needed. But if this is achieved, and then one is in an ideal situation to address the appearance disappearance tension, and eventually probe concepts like the non-unitarity of the mixing matrix, non-standard interaction in neutrino propagation, and also Lorentz invariance and CPT violation. And of course, ultimately address the question of light sterile neutrinos. Indeed, a possible setup for such an experiment was investigated and proposed, finding that indeed the Newstorm facility could really provide an ultimate answer to the question of the existence of light sterile neutrinos. So with this statement, let me come to my summary. So I have tried to convince you, hopefully I did, that our present understanding of neutrino interaction in the few GeV regions would be extremely improved by new precise measurements of, if possible, both elementary targets and heavy nuclear targets. And if this can be done in a Newstorm facility, taking advantage of the very precise flux of both electron and muon neutrinos that can be delivered. Provided, however, I should stress that the excellent flux is complemented by equally excellent detectors. Otherwise, because with such a flux, the systematics would be coming mostly from the detector. Such measurements would have a high impact on the neutrino oscillation program, but would also lead to progress in hadron and nuclear physics. There is also the potential to discover or constrain some kinds of non-standard interactions and even more exotic processes. And finally, as just mentioned, the experiment like Newstorm with two, a near and a far detector in this case, will be in the position to either discover light sterile neutrinos or exclude them with high significance. And this is all. So thank you.
Thank you, Luis. So here there's a question from Cagliari, Francesco.
Luis, there is since in this workshop we are discussing also the possible implementation of both InnoBet and Newstorm at CERN. really, I would like to follow up your last sentence about the detector, because I have seen that you put a lot of emphasis on the reconstruction of the final state particles that points toward the high granularity detector, while maybe for the sterile neutrino search, this is not strictly necessary. So I really want to have your opinion on what would be the best suite of detectors to carry on the program of cross-section and in particular final state interaction reconstruction.
Yeah, well, I am not really an expert on the detector development, and I can assure this is under discussion in NuStorm meetings. What would be the best detector? All I can say is of course, it would be a shame to have such an excellent flux and not being able to explore final states. So one would need really would be really critical to be able to detect protons in the final state, but also pions. I think that would be a minimal requirement for the detector. Again, would be very nice to have not just one target, but more than one, to be able to make see some target mass dependent studies.
Okay. And then I see the point. And then also I have another question. So the story of the reconstruction of the energy, as we have seen from the presentation of Fabio, for instance, even in INUBET, that is a narrowband beam, we cannot go below 10% typically, or so we will be able to measure the energy of the neutrino. Okay, at 5% if the energy is large, but for instance at 1 GeV we will exceed 10%. So again, having a facility that is able to measure on event-by-event basis the energy of the neutrino at 10% level would make a difference in the convolution of the flux in cross-section and in general for the determination of the cross-section, or is still too high?
Well, I think it would be a step forward, definitely. Yeah, obviously, I mean, even for oscillation experiments, even if it looks well, 10% is not so much. But in an oscillation experiment, you have near and far detectors, which also help in the tuning. So yes, I think that at the level of understanding better cross sections, a 10% level would be a good step forward.
Okay.
This is at least my impression.
Thank you.
Okay, unless there are urgent questions, maybe we could.
Andrea.
Yes.
Sorry. No,
Ken.
it's okay. I had my hand up and then I took it down again because Francesco asked my question. But I think I just wanted to say, because we work together now, or rather this meeting is together, what we begin to do is to try and understand the specification for a detector. We want to work through different channels in order to work out properties that we really need to have in the detector. The emphasis on final states I also take away from Louis' presentation. And maybe this is a place where we should be, INUBET and NuStorm should be working more closely together, because I suspect that those specifications are going to be very similar. So like it's an invitation, maybe we can talk to each other a bit more on those issues. Yes.
Yeah, I don't see why the detectors have to be drastically different.
People get possessive, but at least at this stage, perhaps we can talk about the specification.
Yes, I agree. Sorry, Ken, I hadn't seen your hand. So next talk will be given by Fabio Jacob from Padova University and INFN, and he will tell us something about detector R&D for the instrumented decay tunnel.
Hi everyone, can you hear and see me?
We can see you.
Okay.
Try to share the slides.
Yes, and now I think you should see full screen my slides, correct?
Yes. perfect.
Okay, perfect. So I have a little bit of a problem. I would like to minimize. Okay, fine. So my talk is about ENUBET and specifically the detector R&D for the instrumented decay region. So you have already heard 2 talks ago from Fabio Pupilli, and you should be comfortable about some general concept of the ENUBET projects, but let me go through the main points quickly, and then let me jump into the more specific material. So just to remind you, but very quickly, the ENUBET started in 2016 as an ERC project and got to be years later in 2019 a CERN neutrino platform experiment. But from a hardware point of view, the main output will be the so-called demonstrator. Demonstrator because it is a portion of the active decay region. So its purpose is to demonstrate that this technology of an active decay region is scalable up to tens of meters in order to obtain a full decay tunnel. So this demonstrator will be exposed in 2022 at the Proton Synchrotron at CERN. So this demonstrator, and in general, ENUBET goal is to reduce the uncertainty on the neutrino fluxes to the percent level, and the motivation is also found and supported in the European Strategy Particle Physics document in page 5. And it is to this flux uncertainty reduction will enable better cross-section experiments. So I've spoken about this active decay region. So this is the design concept. We want to tag in this decay tunnel the positrons and the muons from kaon decays. And you can see in the figure a schematic of this decay. And in order to enable also the muon tagging, a muon monitor is put at the end of the line. There's a constraint on the timing resolution we need, which is of 0.2 of a nanosecond or 200 picoseconds. So you can see that this will enable the tagging of on a neutrino by neutrino basis of positrons and muons from kaon decays, as well as muons from the resulting pions as well. So this slide is only to let you know where the active decay region is displaced along the beam line. It's after the focusing and bending section, and of course before the hadron dump. So this R&D talk focuses in this green portion of the beam line, and you will hear from Michelangelo a more specific talk about the whole beam line. So this is a rough timeline of the project from an R&D point of view. So starting from 2016, which is the start of the project, the R&D was driven by the construction and prototyping of different calorimeters. This let us, I mean, the ENUBET team, to make trials and errors on the various schemes And let me remind you the most important calorimeters we tried along the years. The first one is a Shashlik one, which suffered from a problem, which is the radiation was rather high in the electronics part. The electronics was too exposed. In fact, in order to assess this exposure in 2017, a neutron irradiation campaign was held in INFN LNL laboratories near Padova. And later, the silicon photomultipliers exposed to such neutron radiation were evaluated. The result was that the signal was degraded, but still the intercalibration spectra were still obtainable. Later, we moved from the Shashlik calorimeter to a lateral readout calorimeter in order to decouple the scintillating and still part from the electronics, and this decoupling was permitted by using optical fibers, which you can see in the only photo of this slide. You can see these greenish optical fibers. And this calorimeter was exposed at CERN PS in September 2018. Then starting from this calorimeter, we gained much knowledge about the problems we got with this specific one, and we are now developing and finalizing a new scheme which will converge into the demonstrator, which will be exposed at its turn at CERN in 2022. So this is a rough timeline, but I wanted to let you know this timeline is filled with different calorimeters. This is the point of this slide. So these were some general concept or introduction. Now let's jump into one of such calorimeters, namely the lateral readout calorimeter. So the lateral readout calorimeter is a rather complex object, and as many complex object is built starting from a brick, from a modular unit, which we call the lateral compact module, or LCM. So an LCM is made of 5 couples of alternatively displaced still absorbers and scintillators. Then each scintillator is coupled laterally, that's why we call this the lateral compact module, by 2 optical fibers that collect the signal. And you can see from 5 scintillator times 2, you have the 10 optical fibers bundled into a 10 fiber bundle, which is put in front of the silicon photomultiplier, this IPM, which converts the light signal into the electric signal, which can be digitized and saved for further analysis. So the steel tile are 3 times 3 times 1.5 centimeters cube, and the scintillator tile instead is 3 times 3 times 0.5 centimeters, and are made of EJ204 from Elgin. Just remind a number, which is the emission peak, 408, so roughly 400 nanometer, so it emits in the blue. I say this because this bluish light is converted by the wavelength shifting fibers. We used for this calorimeter Kuraray Y11 and Saint-Gobain BCF92, which push the nanometers of the light from 400s towards the 500s, so 476 and 492 nanometers for the two models, in order to better match the sensitivity peak of the silicon photomultiplier. That, in this case, by advanced, the model is AST RGB4SP, which is just a name for saying it's a 4 × 4 mm² model, and it's peaked in the RGB, so 550 nanometer. There's a number I would like you to remember, which is the cell pitch, 40 micrometers. I tell you so because we'll see some saturation effects and how we want to decrease this cell pitch in order to enable a less saturating detector. So the lateral readout calorimeter, as I said, is made of this brick, the lateral compact module, repeated many times. So you can see in red a lateral compact module. If you repeat it by 7 times, you obtain like a line or an array, if you like, of 7 LCM. And putting 3 of this array, you have a layer which you want to repeat 4 times in depth in order to obtain a bulk of scintillator and still, which can intercept the positrons, the muons, the pions, and all the particles. This bulk can intercept the particles along the, of course, the beam direction, which you can find on the right of this slide, indicated as the Z direction. So you can imagine the particles intercepting the bulk of this calorimeter, and as you can see, the fibers are decoupling the electronics from the still and scintillator part. So we are now thinking about intercepting this bulk of the calorimeter with positrons, which are the signal, but also with background and specifically neutral pions and charged pions. So we can discriminate between the positron signals and the pion background by watching the topology of the events, or else said, how this calorimeter fires its LCMs. So let's consider firstly the signal, so a positron. A positron is intercepting a doublet of tiles known as the gamma Vito, which I'm sorry I forgot to mention from the previous slide. You can see the gamma Vito doublet tiles in green, so to the bottom right of this figure. So a little bit different, let's say, from the main bulk of the calorimeter. So these doublets are fired by the positron, and then an LCM is designed to stop a positron. For this reason, we can see only one LCM collecting light. So gamma Vito plus one LCM means a positron, so a signal. Then there is the case of neutral pions, which converts into gammas, and in the gamma Vito. And the then the pair, the electron-positron pair resulting from the gamma leaves in the gamma-Vito doublet a signal which is doubled with respect to the positron case. So a doubled signal is considered a Vito because this is a pair. And this is important because the electron and positron pair would stop in just one LCM. So without the gamma Vito, positron or positron electron signal would be difficult to distinguish. So the gamma Vito instead permits us to discriminate this pion, neutral pion background from the positron case. Then maybe easier to understand is the charged pion case because it showers in the bulk of the calorimeters and simply fires a lot of LCM. Well, a lot, typically on average 8 LCMs. So easier to understand how you can discriminate between positron signal and charged pions. Okay, so all these things were put into practice in September 2018 during a test beam which took place at CERN PST9 beam line. The beam was a mix of electron, muons, and pions in an energy range between 1 GeV and 5 GeV. In order to assess how the calorimeter responds to different angle of impinging positrons, the calorimeter was tilted at well, 0, which means no tilt, and then 50, 100, and 200 millirad with respect to the beam direction. What we learned from this test beam? So we can consider firstly the energy resolution, and the plot on the left with the blue dots are the Monte Carlo simulation points, and instead the data points are in red. This is a plot of energy resolution. And at 1 GeV, we have around 17% resolution, which was fitted with a quadrature sum of a stochastic term. So this S in the formula in the green panel, plus means a quadrature plus, a constant term. 17% at 1 GeV is a rather good news because the constraint was evaluated as 25%. In order to separate between positron and pions, we need less than 25% energy resolution. And luckily we got it. But there's still a problem, which is the discrepancy between the blue points, the Monte Carlo points, and the red points of data. So how can we explain such a discrepancy between simulation and data? We need to remember the 40 micrometer of the cell pitch of the IPMs, which gives a limit in the number of cells of this IPM that can fire. And of course, if you put a limit on the number of cells that can fire, you would encounter at some point a IPM saturation, and the saturation is the cause of such discrepancy. So you would imagine, ideally, that if you have a perfectly linear CPM, which of course does not exist, the number of firing cells would be the number of photons corrected for the efficiencies and so on. But it is not the case, of course, because an ideally linear CPM does not exist, and instead you have a CPM which firstly have problems given by crosstalk, which at a given operating voltage was rather high, so 44%, which increases the number of firing cells. So you have the formula on the top right, the number of photons, of course, corrected for the efficiencies, is not multiplied by 1, but by 1 plus this probability of crosstalk, which is 0.44. So you are increasing the number of firing cells, so you are pushing towards the saturation with the crosstalk. Plus you have a limit given by the cell put in front of the fibers, which were estimated to be around 5,000. So this is a limit, and you will encounter saturation. So you cannot have an infinite linear law in the SciPM. Instead, you have an exponential one in which you can see the important number is n max, so the limit of possibly firing cells of the SciPMs. So if you consider this SciPM saturation, we found that we were able to explain such discrepancy, and you can also see in the plot here that the blue dots, so the Monte Carlo points, are moving into the green points considering the saturation, which better match the data, especially at high energy, so to the right of the plot, where you expect saturation to take place. So another, let's say, milestone of this colorimeter was the test of the Gamma Vito. The Gamma Vito consists of tiles, tablet tiles of scintillator put apart 7 centimeters one another. And we were able to distinguish this, you can see on the right figure, 2 blobs fundamentally, which are the positron signal on the left, and instead electron positron signal on the right. So you can easily imagine that these 2 blobs are not fully separated. In fact, there is no white region between the 2 red blobs. So there's some interference between the 2. Else said, this limits the selection efficiency, or if you like, the background rejection. Because if you consider the left blob, so the 1 MIP signal corresponding to the 1 positron as the signal, you can find this number. So the selecting efficiency of the 1 MIP signal is 87%. And instead you have 89% of the background rejection, where background is the 2 MIP signal, so the right blob, corresponding to a purity of 95%. So now let me introduce you to the demonstrator, which is, let's say, the larger hardware output of the NUBET project, and that will be exposed at CERN the next year. The demonstrator wants to demonstrate, in fact, the feasibility of lepton reconstruction, and the important part is that we want to demonstrate it with a technology which is scalable, because in the end, we need to have tens of meters of this technology in order to arrange a decay tunnel. So the demonstrator is much less than a decay tunnel, of course, not only because it is limited to 165 meters, but in this demonstrator, we also limit the azimuthal angle to a quarter of a circle. But the dimensioning of this and the stability and the design of this demonstrator is such that it will be easy to cover the full circle, repeating in some sense for demonstrators rotated one another by a quarter of a circle. There is one more limitation, mainly due to costs, which is we don't fully instrument with sapiens, electronics, and so on, the whole demonstrator, so 90 degrees azimuthally, but instead we instrument it only in 45, in the central 45 degrees, and the rest of the structure is kept for mechanical considerations. You can see in the top left figure the layout of the demonstrator, where in green there is a borated polyethylene shield in order to shield the neutron that otherwise would damage the electronics. And you can imagine in this green part, the fibers would run from the scintillator and steep part up to the silicon photomultipliers. This shield, you can see in the brown panel on the right, would be of 30 centimeters because we estimated with a Fluka simulation there is a 18 factor of neutron reduction. And this polyethylene is as well borated in 5% in order to increase the neutron shielding. Then in the gray panel in the bottom left, you can see how a steel arch looks like, and instead how a borated polyethylene, so a neutron shield layer, looks like. You can see in the borated polyethylene, you can see some grooves in which the optical fibers would be displaced. So let's speak more about optical fibers and specifically how we change the scheme of the scintillator to fiber coupling. So I've spoken about the lateral readout calorimeter, which takes its name from the lateral coupling of fibers to the scintillator. You can see in the top left gray panel. And instead, we want to move to a frontally coupled fiber scheme in the bottom left orange panel. You can see two simulations of how the light collection changes between these two schemes. So the right simulation in which the light is collected on the edges is, of course, the laterally coupled scheme. And you can see instead that the frontally coupled scheme, which is the left one, has a more uniform response because you don't collect light only on the edges. And this uniformity was optimized by putting apart the two fibers by 1.5 centimeter. And even the uniformity was checked with cosmic rays data, and you can see how a single tile responds to cosmic rays in the bottom right figure, and it's rather uniform, as you can see. And we played with this new scheme with a small prototype named Enubino, in which we arranged these frontally coupled scintillators, and we run the fibers through the 30 centimeter borated polyethylene, which you can see in the top left figure on the left. And then you can see in the photo of Enubino, the fibers are not coupled to CPMs in this photo, but now they are. In fact, I acquired data with this prototype. In the finalization of the fiber routing, we'll use a cap which is 3D printed, and that you can see on the bottom right orange panel. This is a rather let's say strange shape. That's why there is need for a 3D print. And you can see how the fibers are collected and comes out of this cap in 3 bundles. So with this Enubino small calorimeter, which is in the end a azimuthal unit of the demonstrator, if you like, we took measurements, and now you can see in the top left figure how the fibers converged into a CPM. You cannot see in this figure the cap I was speaking previously. And we put it in a dark chamber with 2 scintillator triggers named trigger top and trigger bottom, which in fact provided the trigger signal or a cosmic ray is passing there. Then we collected instead the light scintillating in Enubino with a CPM which was amplified. And you can see both the trigger signal in magenta and the Enubino amplified signal in yellow in the bottom right figure. This is fundamentally a screenshot of the oscilloscope. So last part, I've spoken about the calorimeters, but of course you need to read these calorimeters, and even to read the calorimeters we are developing electronics board which are rather custom, and the main characters of these electronic boards are an ADC board equipped with 4 ADC sampling at 250 megasample per second and having 14 bits. And then a logic or digital board that handles these ADC units. And you can enjoy the view of an FPGA in the center of this digital board, which is depicted here in the photo. Then, as I already mentioned, there is this problem of the saturation of the CPMs, which in the end comes from the number of cells available in each CPM. Of course, there is a very easy way to increase the number of cells, which is simply take a smaller cell. And in fact, we studied with Enubino different possibilities, and in the end we decided to have a SciPM migration from a 40 micrometer cell SciPM to a smaller cell, so 30 micrometers. And these measurements took place with the setup I have shown in the previous slide, so with cosmic rays, but also with a blue laser. So let me draw the conclusions from this presentation. EnuBet wants to probe this possibility of a monitored neutrino beam. And the hardware way to do this is build a demonstrator. In order to build a demonstrator for a scalable technology up to tens of meters of an active decay region, of course, you need to do trials and errors before, and that's what we did with different schemes of calorimeters, namely a Shashlik one, a lateral readout one, and now an Ubino, and tomorrow the demonstrator. The R&D of these calorimeters was driven naturally by some core aspects such as the fast timing, the energy resolution, and then we found out the radiation tolerance specifically from neutron, and also the scheme in the fiber coupling and routing, and as well as mechanical stability, especially in the final demonstrator, which will mount 75 steel tiles that weighs a lot. And this demonstrator is somehow the final hardware output of the EnuBet project. And we'll see its apical moment the next year when we'll expose to particle beam the demonstrator at CERN, and we'll see the results. We hope for good results, of course. And yeah, I have finished, so.
Okay, thank you, Fabio. Are there questions? Okay, maybe remotely somebody. I don't see Zoom actually. Can you? Okay, no. I think we can proceed then with the next part. Thank you again, Fabio.
Bye.
Michelangelo Pari from Padova University and the NFN will talk about the beamline.
Hello, can you hear me?
Yes.
Okay, perfect. So let me share my screen. Okay. So you should be able to see my slides.
Yes.
Okay, perfect. So I will start. Hello, everybody. I am Michelangelo Pari, and I will present here the development and optimization of the EnuBet beamline. You will see also from the next talk joint work on the two beamlines. So here I will focus on the EnuBet one. I will start with a very brief introduction. You mostly already saw all of this, but it is important for the sake of this talk to remember that EnuBet is a narrowband beam, so we have a design momentum at 8.5 GeV with a secondary momentum byte of 5 to maximum 10%. So another important thing to remember here is the signals. As a signals, we have, of course, positrons from K3 decay, and also muon from recently from K-2 and K-3 decay. You can find a complete overview of EnuBet from the talk of last Tuesday from Zuya. So, okay, this just to put things in context. One reason why we need such a narrow beamline, band beamline, is also to be able to exploit the narrow band of axis technique. This would allow us to correlate directly the impact radius at the neutrino detector with the neutrino energy. Okay, so here you have just an overview of the most prominent working packages of EnuBet. You already saw some of them detailed, like the last presentation from Fabio about the detectors, and the initial presentation from Fabio Billy about the systematics and the performance. So in this one, instead, I will focus on the beamline, as I said, and in particular, I will give an overview of the baseline design that we currently have of the beamline, but also some recent results on target optimization, studies on the proton extraction, magnetic horn, and needs optimization, and then also some further tuning of the baseline beamline that we are doing. And lastly, I will touch the multi-momentum beamline that we are developing right now. Okay, so this is just an overview of the baseline option of the beamline. So most of its component, most of its design has been completely simulated and ultimated. So the only open things are the evaluation of the full systematics. You will see more details on this from Antonio in a later talk today, and also the engineeristic studies for the proton dump that you can see here. Of course, if there is an overview of the current beamline. And in particular, one thing to keep in mind is that, of course, this beamline relies on slow extraction. This is quite important for us because actually we have important limits of pile up in the decay tunnel because, of course, it's instrumented, as you see in the more detail in the previous talk. And so differently from the majority of neutrino beams, we can only afford a slow extraction, which by it we means a few seconds of extraction from the protons from the synchrotron. In this presentation, I will assume as a candidate, as a driver for NOBET, the CERN SPS. This is a very good candidate for us because it would provide 400 GeV protons. We are assuming here a 2-second extraction speed, but NOBET is still set independent. So other possible candidates that could provide a proton source are the main injector, or also the main ring from J-Park. Going on, so here we go in more details on each of the topics that I summarized initially. So first of all, this is the baseline design of the beamline that now converges to a good result. And all of this process was based on a design and optimization of the optics based on transport by optimizing the optic functions. And then iterating this, of course, with an extensive simulation and validation using particle interaction and tracking programs like Gen4 beamline and Gen4. This is particularly important because we need the information on the backgrounds that will arrive at the tunnel. You can see here some distribution of particles, both entering the tunnel on the top and also hitting the tunnel on the bottom. Particularly problematic are, as we were mentioning initially, positrons and muons, because, of course, as I said in the first slide, positrons and muons are exactly the signals that we are looking for NOBET. And after several iterations in the design of this beamline, we found that tight collimation plays a very important role in let's say, maximizing the signal-to-noise ratio. There are here 2 little snippets that show some example of the collimation we have. For example, we placed what we call a positron filter. So it's a tungsten foil just facing the target that is used to suppress the positrons that directly escape from the target. But also we have these collimator blocks just in front of the tunnel in order to shield and suppress as much as possible the halo and the ground coming from the beam. So okay, this baseline design has also been fully simulated in terms of irradiation, both for ionizing charged particle, but also from neutrons. You can see the 2 plots, top and bottom, gray dose, and here instead we have the neutron dose in neutrons by centimeter square. The hottest point of the beamline is near the first quarter ball and the first collimator. You can see it here. While we also found some good solution in order to shield as much as possible. For example, the electronics, as Fabio detailed before, we have a shielding in borated polyethylene that was able to reduce the dose to the electronics and the silicon photomultiplier to a factor 18. Similarly, we modeled the hadron dump layered with borated concrete for the same reason, an iron and a graphite center. One interesting thing that came out from this study is that you can notice here that the level of dose that the second dipole is getting is significantly lower than the first one. And this actually would open the possibility of using the second dipole instead of the second dipole, let's say a superconducting second dipole. So This would bring several advantages, like, for example, a more pure neutrino beam. And so this possibility is currently being investigated by the ENUVET collaboration, and we will have more results soon. So going on with the targets, we performed recently a target optimization that was based both on Fluka and on Gen 4 beamline. And we came out with two possible good candidates. First of all, we have a graphite rod of 70 by 6 centimeters. This, of course, graphite is a well-studied material, and this implementation would be feasible. The performance was also good. It's placed on the optimum here of this orange line in the plot. And for these reasons, this particular target has been chosen as the target for the beamline design that I've showed up to now of ENUVET. But the other interesting solution that we found is an Inconel rod of 50 centimeters by 6. This is a relative new material, new solution, sorry, for a target, but it's also being considered by NuStorm. And in particular, we observed some interesting results because there seems to be a reduced number of positrons and a different distribution of them. And so actually this target is being considered for alternative beamline design that I will show in the next slide. So you can see some fraction of the particles produced by the two targets, and here some distribution in the radial space. Okay, so putting all of this together in the baseline design of the beamline and using the new optimized graphite target, we were able actually to increase the kaon flux by a factor 2 with respect to the previous version of the beamline, and also to reduce the positron background. So with all of this, and assuming a 500-ton neutrino detector placed at 50 meters from the decay tunnel, we would be able to gather 10 to the 4 charge current electroneutrino events in about 2 years of data taking. So by summarizing the results on this baseline design of the beamline, so we reach a good performance, and the design converges to a successful result. And also this beamline is fully based on slow extraction. So this has important advantages because it makes it more cost effective, because up to now it's fully based on standard magnets, so normal conducting magnets. And the operation would be supposed to be stable, and also the rate at the decay tunnel is the lowest possible given the design. But anyway, the potential flux increase that we would get from the use of a magnetic horn is appealing, and we can't ignore it. So the only thing to keep in mind here is that we cannot tolerate a fast extraction, and by fast extraction I mean tens of microseconds, the typical length of a fast extraction of primary protons. Okay, so to this end, what we did was instead to start a dedicated study in collaboration with the CERN SPS in order to try to develop a horn-compatible slow extraction. You can say in the top plots here, these are actual measurements we took in the SPS. And we were able also to implement this pulsed slow extraction. We called it burst mode or burst extraction. And we were also able to show that it can be optimized in operation. Here we are fitting the pulse into a 10 millisecond square wave. While from a simulation campaign, instead, we were able to show that it would be possible to fit, let's say, the length of these pulses between 3 to 10 millisecond range. And one thing to stress here is that this extraction method is totally general, and it could be used for other application beyond ENUVET or a horn. For example, if we would need to increase the cosmic veto. In parallel, we also performed some dedicated study on the nominal slow extraction, so the flat one, in order to try to optimize it as much as possible and smoothen it as much as we can. You can find all the details in these two references about these studies. Okay, so going on from the successful results about the extraction scheme and the pulsed slow extraction, we started then opening the possibility for our, and all this, of course, had several steps to perform that are all completed now. So first of all, we developed a full simulation based on Gen 4 of the magnetic horn. You can see it here. After that, we also developed several geometries in order to try really which one was the best for us. So the mini boom style, double parabolic, but also a conic. You can see some of them here. And after this, of course, we need to optimize this device because it has many parameters. And we decided to go for the genetic algorithm, which seems to give good results for this type of problems. Also, NuStorm did a similar optimization. And of course, this also allows us to keep some common hardware constraints for a horn enforced during the optimization. So all of this was inserted into an optimization framework that we developed in order to carry out fully automatic optimization using a computing cluster. You can see here some convergence plot take more or less between 100 and 200 iterations to converge. This typically doesn't take more than a week. So yeah, so after all of this, the first result, they refer to what we call a standalone optimization of the horn. And by standalone, there is a little sketch here. Basically, the figure of merit, which is the number of kaons that we are able to focus, of course, inside the momentum byte of NUBET at the first quadrupole. This we did in order to be as much independent as we can from the rest of the beamline. And using this figure of merit, we were able to prove that we could arrive consistently to a factor 3 of gain in this flux. Of course, one of the latest and most promising solutions is using the Inconet target. You can see it sketched here. And thanks to the fact that this target is very short, it could be placed completely outside of the horn without losing the gain, and all the constraints that we placed in the horn parameters were enforced. So, of course, the gain from the horn comes from the squeezing of the angles of the particles from the target due to the focusing power. You can see some angle distribution here. But of course, this comes at a price because the dimension of the beam and of the phase space changes significantly. You can see here the radial phase space, here the actual phase space, the radial distribution, and the actual phase space here. So the main problem was that the current version of the baseline beamline that I presented up to now is not optimized or designed for this type of beam. So the next step was to start the development of a dedicated own version of the beamline, so in parallel to this. And for sure, significant changes will be required in order to exploit at best this device. You can see here there is a big mismatch if we use the same beamline comparing the envelopes. Okay, so basically the roadmap of this project, I summarize it in 3 steps. So the first one is already completed. We have developed a new framework based on MADEX for the optimization and design of this beamline. It is possible also to track particles using PTC. So this should be an advantage, and the process of the optics design should be faster. And then, of course, all of this has to be validated with particle tracking and interaction codes. So we plan to use Gent4 for this, and we have to then compare it with the baseline design, of course. And the final goal is that we would like to prove that we can maintain this substantial flux increase, but also we have to still enforce the narrowband constraint, so the beam has still to be narrowband, and also we also have to enforce, of course, the requirements of the bank account at the decay tunnel. We're sure we will raise a bit, also given by the pulse operation. So if all of this is confirmed, then we could proceed with the implementation and the R&D, especially for the horn itself. Okay, so directly from the study we did on the horn, we were able to upgrade the optimization framework that initially was hardwired to the horn problem in order to make it fully generic. And so in this way, we are able now to apply this optimizer to any, let's say, optimizable multidimensional problem that we have in the beamline design. So as a first application, we decided to apply this method to fine-tuning the collimation of the baseline version of the beamline. So you can see it here. We started from a reduced problem. So here we have the last section of the beamline. We are fine-tuning the collimation with the optimizer here. It's a 5-dimensional problem. But the first results are already promising because we see, for now, everything is still ongoing, of course. We see an interesting background reduction. You can see from the top plots here that in red we have the optimized beamline, and in blue we have the initial one. And these plots refer to background particles hitting the tunnel, of course. And instead, down here in the bottom plots, we have the signal particles. So they remain quite unchanged, and then this seems very promising. So we will have soon more results on this, and we can also apply all of this to different problems or to more extended problems. There is a convergence plot here, typically converts in 100 of iteration, can take some week. Now we arrive to the last part of this talk. As it was reminded by this early morning by Fabio, the average energy, the peak energy of the electron neutrino spectrum of NUBET is around 4 GeV. So this would fall in the dune region of interest, as you can see here. But it would be useful actually to be able to cover the full range of interest, both the full one of dune, but also the one of hyperkernel. And so to this end, recently we started a dedicated study that focused on the development of what we call a multi-momentum beamline. This now is in collaboration with CERN, particularly with the EA section. And of course, the goal is to build a beamline in which the energy of the secondary particles can be changed in order then to cover the full range of interest for the neutrino energy, in particular arriving also to the hyperkernel one. So we have already a first version of this beamline. So the optics have been designed using transport, and instead the fluxes now are being computed using Gen 4 beamline. You can see here a model with Gen 4 beamline. In particular, the geometry and the implementation of the magnets is all based on existing CERN magnets for now. You can see in red the dipoles into the quadrupole. Here there is the momentum collimation here. So for now, the first results on the count fluxes of this beamline are promising, but still we are waiting for the full study on the background, of course, and systematics that will come later. Okay, so I arrive to the conclusion, and I will start from the baseline option of the beamline. So the main design phase for this version is terminated, since all the simulations are nearly to completion, and a satisfactory performance has been reached. Of course, the results are good up to now, and on this we are on schedule. So the last thing that will be released will be the systematic on the full systematic on the neutrino fluxes, and you will have more details on this in the talk from Antonio later. Concerning instead the non-baseline option, they proceed as planned, but they are already pointing to some promising results and potential improvements. So first of all, we have now the ongoing investigation on the use of a superconducting dipole, and this came from the good results of the estimation of the doses in the baseline option of the beamline. After this, we successfully developed this pulsed version of the slow extraction, and this opened, let's say, the study of the magnetic hole. Of course, then for this study, we developed the full simulation framework, genetic optimization, and it pointed to a standalone gain of a factor 3. So following this gain, we are now working on the development of a dedicated beamline. And finally, we are applying the very same genetic optimization also on the baseline version of the beamline, with the goal of increasing the signal to noise ratio. And finally, of course, there is the multi-momentum beamline that you just saw. So all the fluxes, updated fluxes and spectra with all of these alternative designs will be available by 2022. So this concludes my talk, and thank you very much for the attention.
Thank you. Thank you, Michelangelo.
Welcome.
Questions from Cagliari or remotely? Yaroslav has a question. You can talk.
Hello. I have actually many questions, so I may suggest that if it's possible, we could actually chat on the Zoom after my talk, maybe.
Yeah, that's
however, I would like to ask about this multi-momentum beamline.
okay.
What are the goals? What are the momentum bytes you want to obtain, and what is your strategy of achieving that?
So here in this plot on the top, actually, you can see the momentum that for now we are considering. So we have 8.5, which is the current one of NUBET. But then we're also considering 6 and 4. Then, of course, the process is ongoing, but for now, these are the ones that are mostly being considered. I also can make you in contact with the person which is currently working full time on this. But these are, for now, these are the momentum we are considering. And yeah, we can chat later for more details.
But not simultaneously, there you will have different settings for 8.5, 6, and 4 GV/C, right?
Yeah, of course. Yeah, I think the plan is to be able to, of course, change the optics, so the powering of the magnets. But I don't know if there is a plan also to change then the positions. We'll have to see with that. But of course, the beamline will have to be mostly the same. But yeah, what can change are the powering and maybe we can slide some magnets or collimator. So I guess these are the point of leverage. But yeah, for more detail, we can actually involve also.
Maybe if I can add a comment, really the idea that raised the activity on the multi-momentum beamline would be the possibility of achieving this range using the same components and just touching the currents of the dipoles and the quadrupoles. There might be adjustment on the collimators, but the general idea is that the beamline will be flexible enough. I must say that we have not presented this because they are preliminary, but the preliminary results indicates that we can cover this range using the same optics. Then, of course, we will have to go through the job for the background reduction, so for the optimization of the collimators.
Thank you.
So Jaroslav, I think you can keep the stage and present your studies for a possible common beamline for InnoBet and Storm.
Okay, I think I cannot yet share the screen. Oh no, I can. Thank you very much. Okay, so you should be able to see my talk now in the full screen mode, I believe. Maybe not yet, not now. Can you confirm that?
Not yet. Now, yes.
Okay, so I will talk today about the work which I did a little bit over the summer with my summer student from Vietnam, who was working on the CERN summer studentship program. And that work, that idea was already proposed at various meetings by various people before, but I wanted to investigate if there is a possibility to have a common beamline to run InnoBet and NuStorm simultaneously. So just a few words of introduction. A NuStorm, as you know, is using the beam from high energy proton accelerator, proton beam hitting a target where pions are produced, and pions are injected continuously into the decay storage ring with long straight section, where the pion beam decays in such a way that some part of the forming muon beam has significantly lower momentum and can be made circulating in the ring for many turns. So that can actually allow for a continuous injection of beam, quasi-continuous injection. The only point is that you would like to separate the signal from neutrinos from pion decay and from muon decay, and that's why we would rather wish to have a pulsed operation mode so that those can be easily distinguished by timing in the detectors, because the pion signal will be on during the injection, while the muon decay signal will continue for several tens or even 100 of turns afterwards. So then the NuStorm will be equipped with series of near and far detectors, which then will be used for neutrino physics experimentation. The NuStorm is fed by pions produced at the target and transported into the into the storage ring using conventional beamline and conventional target and capture system based on the horn. And we have several designs for this, at least two for this transport channel, and there have been recently quite significant progress in the simulating of this beamline from the target until the injection, and including the quad channel. My student is working on that. This will be presented in the near future, but not today. So one of the important aspects is that the SPS at CERN can be used as the proton driver for NuStorm. And the NuStorm can address significant issues with systematic errors for long baseline oscillation experiment for like Dune or Hyper-K. And can in particular measure neutrino cross sections precisely. That has been already discussed in previous presentations. The NuStorm can also be used to search for a long-standing question of existence of sterile neutrinos, and recently proposed also as the active component of the accelerator R&D for the future muon collider, using the front end of NuStorm as a test stand for the muon collider accelerator R&D. So in particular, we already the seating at CERN has been proposed using the existing tunnels, and both the sites for near and far in the sense of sterile neutrino search option are potentially on the table. So the NUBET, on the other hand, is I have to admit I am not an expert on NUBET. I'm trying to learn new things, especially today. So the NUBET is facility based on narrow band beam to produce an intense source of electron neutrinos. And the key is the instrumented decay tunnel to monitor large angle positrons produced in the free body decay of counts and be able to discriminate them from neutral and charged pions. And what is very important that NUBET can also, together with NuStorm, contribute to a precise determination of absolute neutrino cross section. And also very important, SPS beam can also be used for NUBET, as it is proposed for a NuStorm. So there is an arising question which motivates this study, if it is possible to use the same SPS proton beam extraction and target and capture system for simultaneous running of both experiments in parallel. So in particular, at the end of that study, which just only started really, we want to find a solution where we can optimize a number of pions and counts going to those experiments in various modes of operation, and providing a good suitable optical functions at the endpoints to the entrance endpoints of the beamlines and entrance to the experiments. So what is the basic idea is cartoon kind of is presented here. You have a proton beam from SPS hitting a target where the secondary particles are produced, and after the certain common part of the beamline, the beams are separated and sent to the two experiments. You should not treat this cartoon as an indication of length or anything like that. It is really just to illustrate the idea that from the same target and capture system, you have emerging two beams for the two experiments, which could in principle run in parallel. So the initial assumptions at the moment, which are the only ones we have actually used at the moment, there may be more to consider, is that SPS beam is at 100 GeV kinetic energy sent to the target, which is immersed in the horn. So initially we thought that the simplest idea would be to just use the solenoidal capture system. But that was quickly discarded because the need for multi-GeV focusing for counts or pions for both facilities, for NUBET in particular, but also for New Storm, would require extremely high magnetic field in the solenoid of the order of tens of Tesla, which would call for a superconducting design. Such devices have been proposed for the Muon Collider, but they are considered challenging, and we decided to try first conventional horn as a simpler and more cost-effective solution. But that have a very important consequence, is that this makes the
Okay, so we lost you for some seconds.
Where did you lost me?
Like 10 seconds.
So did I spoken about the solenoid?
Yes, of course.
Okay.
Basically, we didn't miss almost anything.
Okay, so basically we decided to use horn as the more cost-effective and simpler and conventional solution for capture. However, that means that we should operate with the same polarity for both experiments at the time, and the simple sign flipping, which could be possible using solenoids, is not possible, is not in hand. So here we have assumed that the higher momentum beam will be sent to NUBET, and we assume 7.5 GeV over C. You can ask why this value, not 8.5, is because I will explain that in a second. It was just an example for the start of the design work. So we assume 5 GeV over C is a kind of standalone New Storm proposed at the time at Fermilab, and we proposed 7.5 GeV for NUBET. And I saw from the previous talk that different momenta for NUBET are also considered. So that's good, I think. So that makes it consistent with what I'm trying to do here. So both beams would have the same polarity. This is what I mentioned. And in order to separate the two beams and send them to two experimental facilities, dispersion needs to be generated after the target. And this study is only about designing the system which can actually do that. And so the preliminary estimate requires dispersion of the order of 1.75 meter. So the CERN summer student from Vietnam, Ho Quoc Trong, who worked with me, performed the initial design and optimization in Madix. And so the input to his optimization was the parameters of the beam, which we have from the Mars simulations, which was the courtesy of Sergei Striganov from Fermilab, who simulated the in-cornel targets, but with SPS energy of 100 GeV. And here you see the parameters of the beam and parameters of the target, which corresponds to the which we have assumed for this study. So we kept the material or as in-cornel as it was found interesting at the time at Fermilab, and I saw that NUBET is also interested in this material, but we could also consider other types of material as well, so that wouldn't be a problem. So we had a file with spectrum of pions shown on the right, which finishes sharp, quasi-sharply at 8 GeV, because this was the cuts which I asked Sergei to perform at the time. And we don't have counts, actually, we only have pions. For the magnetic design of the system, it does not matter, because counts and pions in the magnetic field will only, the dynamics will be fully governed by the momentum. But that's why we decided to use 7.5, because that would give us a significant bite of momentum around which we can play. So that was the reason why 7.5 was chosen. So concerning the horn, we used the Fermilab design by AOLU, where only the forward part shown on the right, where only the forward part on this picture was used. So on the right from the dashed line, because at the time of the study, this first part was considered marginally in changing the efficiency of transported pions. So we have simulated the magnetic field produced by the horn, but the multiple scattering by in the conductor material is not implemented yet, and it still requires to be incorporated in the future. So we basically, for varying the momentum for the operation of the horn, we just basically scaled the horn, and I confirmed that the optics, the phase space actually behaves accordingly. So it actually scales with momentum. So what was found out that if you simultaneously run the beam of 5 GeV and 7.5 GeV on the same horn with the same setting, you can still have a significant number of particles being focused. So obviously focusing on this horn is only this central part of the plot. And you see that the optical condition is different, but a significant amount of particles still are being affected by the and is focused by the horn. So here we see particles of 5 GeV plus minus 10% and 7.5 GeV plus minus 10%. And horn has the same setting. Then we used the beam conditions which were at the time optimized for 5 GeV pions as the input. And we designed the short lattice, which is less than 15 meters long, which can create the required beam conditions and have acceptance consistent with new storm requirements, which are 2 millimeter physical acceptance. I think this is much more than what is required by NU batch, subject to confirmation. So we aimed to have a fully normal conducting design. However, at the current moment, the dipoles are normal conducting, but some of the quadrupoles needs to have higher fields. So that may need to be superconducting. So the Ho performed the design with the initial conditions he found was optimal for 5 GeV. And he designed the lattice around the mean momentum of the two facilities, which correspond to 6.25 GeV over C. So then I performed the tracking through this system using the large emittance and the cold beam optics, which have implemented routines which allows for very large momentum and very large amplitude tracking. However, the magnets are still in the hard edge approximation. So you clearly see that the 5 GeV and 7.5 GeV over C goes through the beamline. The beamline is opening towards the end. This is where we would switch to the independent beamlines afterwards. This still needs to be designed, and further studies needs to be performed towards allowing different alpha and beta conditions at the start. But we can see clearly the good beam separation at the start. Here we assume this similar, so in the previous plot I showed the tracking using full momentum spread, but just for curiosity, we also studied with order of magnitude smaller momentum spread, and we can clearly see the chromatic effect, which basically means that the optical condition for these two beams are different, which would require different designs for the following transport lines. And so that can also be optimized with a different beam conditions from the horn. So that altogether needs to be further optimized if that would be considered useful. Finally, we also consider that if we have this target as a front end for the NuStorm and NuBet, we could also use this system for feeding the beam into the muon cooling facility. So we studied what happens to 300 MeV/C beam if we tune horn and the first quadrupole to this central momentum, but and reduce the reference momentum of a first dipole by a factor of 3 with respect to 6.25 GeV/C. So that would mean that the dipole would provide very strong bending for the 300 MeV/C beam and can extract the beam, and we could achieve the condition of clearing the second quadrupole. We don't believe that that would allow simultaneous running of 3 facilities, because I think the horn would have a very dramatic effect for 300 MeV/C particles, except only the ones which go forward. And there may be not much going forward because of pions, low energy pions being could be actually strongly absorbed in the forward region by the target. So this has to be studied. We haven't been able to study this because, as I showed you before, my pion beam is between 1 GeV and 8 GeV at the moment, and we should generate the full spectrum again to be able to study that. That is another thing which needs to be addressed. But at least you could imagine of running NuStorm and NuBet simultaneously for in a quasi-continuous mode, which is required because these are neutrino experiments, so they require a lot of running time, while from time to time you could imagine switching for cooling, providing the beam to the cooling facility, which is the R&D experiment facility, which only requires the beam to be sent from time to time. That is what I believe. It should still be discussed and confirmed. So this is my summary. So we have a preliminary design of the first part of a common transport line for parallel running of NuBet and NuStorm with 5 quadrupoles and 4 bending dipoles to generate dispersion for beam separation for to be possible for the 2 facilities. The current design, which initially aimed at normal conducting design, seems to indicate that we would need a sum of quadrupoles to be superconducting. That would be further optimized, for instance, by increasing their length. We also started working on the FFA type lattice for that part, and the results are encouraging, but didn't manage to produce them for today. So I would say that no showstopper was found so far. Further work will include the design and performance studies of downstream parts of the transport line matched to NuBet and NuStorm experiments, optimization of lengths. I am aware that NuBet would like as short transport from the target to the instrumented tunnel as possible. We are at 14 meters, and we would need further elements in order to suppress dispersion and match to the experiment. That may be further optimized with this beamline, so it would be made more compact, in particular if we would be allowed to use superconducting magnets. And also we would need to investigate on the flexibility for different operating modes. So, NuStorm definitely need to scan momentum over the relatively large range. I see that NuBet is also interested in running with different momenta. How that could be combined and optimized is a very interesting question. Thank you. That's all what I have for today.
Thank you, Jaroslav. Extremely interesting piece of work. So there is first of there are several questions actually. So let's try to be concise. Chris Rogers, I think, was the first.
Hi, Yaroslav. Thank you very much for the nice talk. So I guess I have two comments. The first one is for the cooling demonstration, we can do an awful lot with low rate. So the cooling demonstration relies on, for example, quite heavy collimation, both longitudinally and transversely. But for all of the preparatory work, which actually is the majority of commissioning the beamline, for example, we can open up the collimators, or we can turn off the time and energy collimation and do sort of beam alignment studies and things. So that's my first point. So even if the rate is low, coming out of Newstorm, it's probably enough to do a lot of interesting and useful work. So don't necessarily be afraid. But then the other point was, I was interested that you have superconducting, you may need superconducting magnets in the beamline. I wonder what the losses are and whether they can be tolerated by superconductors.
Yes, this is an excellent question. We would like to study the rate when we will have for the continuous mode, when we would have a proper pion and kaon file with a beam at the target, and we will be able to answer your question, how much rate would be provided by this common system. Concerning the superconducting magnets, yes, this is an issue that the power on the target is significantly lower to any facilities have been proposed for muon collider or neutrino factory by at least factor of 20. And the superconducting magnet would not be close to the target. And there will be, as you hear from NUBET talk and also from Newstorm, there would be a collimation system very close to the target to take off majority of secondaries, which will not be captured, because the horn will only be able to capture certain central part of the beam, but all the other part of particles will just still be going through, and we don't want them to go anywhere close to our detectors or even to our magnets. So they will be collimated. So I don't think that that's a very significant problem. Can be mitigated. But obviously it has to be studied in more detail.
Thank you.
Okay, I think Tord was the...
Okay, so as you know, there is also a proposal to use the PS for muon collider cooling tests. And I understood that using the PS beam would not provide enough intensity or beam power for a Newstorm. Is that the case also for InnoVet, that PS would not be powerful enough?
That is probably a question to the NUBET colleagues. I would think that they need 8.5 GV counts, so they would. My guess is they would benefit from high energy from SPS, but maybe they can answer.
Yeah. Yes, actually we are doing studies on this because it's extremely important thing to address. And actually, of course, the pion yields are about linear with energy, so you lose quite a lot of primaries. This means that we should compensate this with maybe a higher acceptance beamline or and a lot of more protons. So it's not an easy answer, but we are
at the same time, access to SPS beams is less, in the sense that it's needed for LHC.
So, Tord, I just wanted to comment. Sorry to interrupt, Andrea, but for Newstorm, we started with the PS and moved to the SPS because of space. So I believe that
because of, sorry, I didn't hear.
Space. Tunneling, interference with other infrastructure.
Right.
So I think we go around the loop again. But the comment that Newstorm can't get enough rate from the PS, I don't believe is true.
Okay.
And clearly we have to quantify.
Fine, thank you.
It's kind of work in progress, let's say.
Right.
Michelangelo?
Thank you. Thank you.
So yes, I had one question about the extraction of the protons, because to what I understood, for Newstorm it would be a fast extraction, right?
Yes, that's right.
Okay. Okay, yeah, because that would be the only, let's say, problematics for us, because as Enubet, we can't rely on a fast extraction, because it would give us too much pile up at the decay tunnel. So yeah, I was thinking if there is a way to solve this, but because up to now we are assuming a slow extraction of 2 seconds, but it can also increase for the baseline option, of course. Of course, we could use the same horn with the pulsed extraction, but that would require, I think, an R&D on the actual horn technology. Yeah, so this is the only thing I think of mind immediately. So.
Yeah, the only answer to that is that this is an excellent question. I have realized that question coming during the previous talk. My short answer to this would be that Newstorm in principle can work with quasi-continuous injection because there is no kicker. The only problem is separation of the signals from pion and muon. So that depends on the time structure of the incoming beam.
Mm. Yeah, then there is, of course, the horn, because I don't think the horn can be pulsed for long times, and actually, yeah, it can. But one possibility, I mean, still keeping the split version of the beam and doing the design very nice, could also be to have a cycle. I mean, not exactly simultaneous, but like either 2 cycles with the splitting, or let's say 2 extractions in the same cycle. This has been already done in the SPS several years ago, in which the beam was extracted with 2 different type of extraction in the very same cycle. So there could be one slow extraction and then a fast extraction at the end, in which at the beginning the horn, of course, remains off. But yeah, there could be a range of solutions. But yeah, I was just thinking about this, because yeah, at some point it will have to be phased.
Thank you very much. Yeah.
Actually, I have a follow-up of this question, in the sense that I was wondering whether there is any hope to run Newstorm with the static option, because as you were mentioning before, Newstorm in principle can run in a semi-continuous mode, but probably it pays a reduction of flux. But since, to best of my understanding, for the physics, you have order of 10 to the 6 new charged current events, even a significant means factor of 3 or 4, let's say, reduction of flux would not affect at all the physics of Newstorm. And of course, it would simplify tremendously, not only the implementation of the Enubet and Newstorm, but also Newstorm by itself, because clearly the horn is by far the most fragile component of the beamline. What do you think, Jaroslav, about this?
Just because this is really the hot topic, and we have a really brainstorming at the moment. The problem of separating the signal from muon and pion decay can be very simply solved if you put your detector along the other straight of the decay ring, where there is no pions. So that would actually make this possible. Obviously, we are limited by the power on target, and then with horn we will, as you know, the rate is being reduced. So that may be a potential problem. But the separation of signals can be achieved if you allow another detectors being placed along the different decay straight. So in principle, could be done.
Okay, that's a very good news. Thank you.
Yes, I definitely agree. So let's move on. Next talk will be about systematics with Enubet, and the speaker is Antonio Branca from Milano Bicocca.
Hi, can you hear me?
Yes.
Okay. Good, I will share the slides. Okay, do you see the slides?
Yes.
Okay, good. In just a moment, I have something. Okay, in this talk, I will present the method that we are developing within the NUBET collaboration in order to reduce the systematics on the neutrino flux by exploiting the monitoring of the leptons. Here is the outline of the talk. I will briefly introduce what are the main contributions to the systematics on the neutrino flux and what are the methods that are used in order to assess those systematics. Then I will move to the discussion about the introducing the lepton monitoring for the constraint on the flux. So how do we plan to exploit the observables from the leptons for the constraining? In particular, I will present some first fit model that we developed for the flux constraint and validation by using some test Tori Monte Carlos. And then I will go to the conclusions and next steps. So in general, as it was also mentioned early this morning by Fabio, the systematics that have a larger impact on the neutrino flux are the one coming from the hadro production and the parameters related to the beamline, so the geometry and the focusing part. And here in this slide, I tried to summarize what are the typical values for Minerva and T2K collaboration. So in summary, the order of magnitude of these systematics is around 10%. And as we have seen during the conference, there are also improvements by exploiting neutrino scattering on electrons and replica target that further improve the flux precision down to about 4 or 5%. So, but the interesting part here is to the way these systematics on the hadro production and on the beamline are propagated to the neutrino flux. I tried to sketch it and summarize through these flow diagrams in these slides. So you here see how the hadro production systematics are taken into account. Basically, we have the simulation of the proton-target interaction that is then fed to the beamline simulation. So we have as output the Monte Carlo events from which we compute the flux, and we can use as input the hadro production data in order to reweight the Monte Carlo simulation for this to take into account this data, and so we get in this way the nominal, what I call the nominal flux. At the same time, we can also input into the simulation the information that we have from the covariance matrix of the hydro production data. And this way we can get a set of reweighted Monte Carlo simulation from which we compute a set of varied neutrino flux. And from this we are able to compute the errors on the neutrino flux. So basically, the procedure is similar to take into account to propagate the systematics on the beamline parameters. What we do is to consider a simulation of the beamline with the nominal parameters values. This way, we get the nominal neutrino flux. And then we tweak the parameters of the beamline within their errors and compute the corresponding plus minus 1 sigma neutrino fluxes. And so this way we get information on the errors coming from the beamline on the flux. So the NUBET facility, so the asset of the NUBET facility is that we have access to the observables, to the physics observables that are measured in the calorimeter and which are related to the so-called taggable component of the neutrino flux. So the neutrino components for which we are able to measure the corresponding lepton in the calorimeter. So this way, by using this information, we can constrain the flux. And the question now is, how do we take into account this information? How do we plug this information in the procedure that I described in the previous slide? So here is a revised version of the flow diagram that I showed before for the hydro production, which includes also the information from coming from NUBET. So basically, so we don't only have the information on the nominal neutrino flux, but we have also the distributions. We can also get the distributions of the observables for the physics observables for the leptons that are measured by the calorimeter. And so in this way, by inputting the hydro production data, we can get the nominal distributions for the lepton observables. And in the same way, we can, by using the covariance matrix of the hydro production, we can get a set of lepton observables distributions from which we can compute the corresponding errors. Again, we have the information from the nominal flux of the neutrino with the corresponding error at the prefit level, so before using the information on the leptons. The same procedure applies for the systematic errors that come from the beamline geometry and focusing. Also in this case, from the simulation of the beamline with the nominal values for the parameters, we get nominal distributions for the leptons observables in the calorimeter. And from the tweaked simulation, we get the corresponding plus minus 1 sigma observables distributions for the leptons. So now we have all the ingredients in order to build a model in order to exploit the lepton information measured by NUBET and to constrain the neutrino flux. basically, the observable distributions, the nominal one and the plus minus one sigma, are the so-called, so what we call the template distribution that we use in order to build our PDF for the model. From this model, we are then able to produce and fit a set of toy Monte Carlo experiments in order to get the a posteriori autoproduction and beamline parameters that we use to reweight the Monte Carlo and to get the reweighted neutrino flux with the corresponding error post-fit, so after including the information on the leptons. So in this slide, you see how we build our fit model. So as I said, we build a probability density function starting from the distributions of the physics observables of the leptons. So using the nominal one corresponding to the nominal parameters, and the displaced one corresponding to the plus minus one sigma errors. And so the PDF is basically a sum of the signal and background shape templates weighted by their by the corresponding normalizations. And the systematic errors on the autoproduction and beamline are described by these alpha and beta parameters, which are our nuisance parameters in the model. So here you see the parameterization of the signal background number of events and template shapes with respect to the nominal values. So these coefficients here, the R and delta T, represent the relative variation of the shape and of the normalization with respect to the nominal values, considering the plus minus one sigma errors. And once we build the PDF, we can plug in we can plug in the model into an extended maximum likelihood to fit our distribution. And in this likelihood, we also take into account the a priori information that we have on the nuisance parameters. So what we have done in order to validate and test the procedure is to build a toy fit model for the neutrino coming from the K-mu signal. We are using RuFit for building the model. This is standard software that is extensively used and tested by the high energy community. We are using a toy hardware production model and the so-called multi-universe method to propagate the uncertainties from other production parameters to the neutrino flux and to the observables. So in this part here, you see the simple toy autoproduction model that we are using. It is parameterized with 3 parameters for which the nominal values are this one here, with a relative uncertainty of 10% and a given correlation matrix. So here it's also summarized the procedure that we are using to get the observables and the flux. So basically, we draw events from the autoproduction model and assign them some mock kinematic variables. And from this, we get one set of simulated events with nominal values for the parameters, and n sets corresponding to different values of the parameters that are drawn from taking into account the covariance matrix. Then each event is reweighted, taking into account these weights that are basically the ratio between the new parameters and the nominal one. And so in this way, we can get a set of realizations for the flux and the observables. So here you see an example of such observables that we get. In particular, it's shown the distribution of the muons impact point along the calorimeter walls in the K mu nu decays. This is the one-dimensional distribution, but we actually use a two-dimensional distribution for the fit model. The red line here shows the distribution that we obtained with the nominal values for the hydroproduction toy model. The blue line distributions here are the reweighted one by coming from a possible realization of the values for the other production parameters, and from these distributions we can compute the error band, so the error on the nominal value, and so at the end we get all the information we need in order to build our fit model. So on the right side, you see the distributions for the templates that we use for the fit model. So of course, in principle, we can also build one template for each other production parameter, taking into account the correlation between the different combination of parameters. This is performed by doing a correlation of the parameters, and then we can sample the PDF by moving along each independent parameter. So this is what we get at the end. So here you see on the left side the distribution for the neutrino energy spectrum. Again, in red, you see the nominal distribution reweighted with the toy production model. The gray band is the error that we get from the propagation of the uncertainties on the other production parameters. And in this test that we performed, it amounts to 15% error. So this is the information that we have before performing the fit. Then what we do is to use our model to fit the data. Here you see on the right side an example of a fit on one of the toy Monte Carlo experiments. So these black dots here show a data set of a pseudo experiment. The color field histograms are our signal templates. And in this approach that is shown here, each one of the color field histograms correspond to the muon distributions related to the neutrinos that fall in one of the beams of the energy spectrum. So the dashed histogram instead is corresponds to the background events. So concerning the signal templates, the hadron production in uncertainties, the uncertainties on the hadron production induces a 15% variation in the normalization with a negligible change in the shape. So the effect between the different templates is completely correlated in this test, in this toy Monte Carlo test. So basically this means that we can fold the effect of the three parameters, of the three hadron production parameters into one nuisance parameter in the fit model. The background template is simulated with a resulting 14% variation in the normalization, with some changes also in the shape. And we are assuming that the variation on the background shape it's uncorrelated with the one from the other production on the signal one, in the signal templates. And so we introduce a second nuisance parameter in the model in order to take into account the systematics on the background. So at the end, in order to study the performance of the fit, what we do is to generate a set of toy Monte Carlo experiments and to fit them with the model. So in this way, we can study the fit bias that you see here. They are evaluated by looking at the mean of the distribution of the difference between the fitted value of the number of neutrinos with respect to the generated one. You see that this value is 0 for all the overall the energy spectrum of the neutrino. And then the post-fit error that we get is evaluated by the width of this distribution, and it amounts in this example to 1.8%. So with this test that we performed using this toy hadron production model, we starting from a 15% relative error on the neutrino flux, we get a post-fit error of 1.8%. So as a summary, what we have done is to develop a procedure for the assessment of the neutrino flux systematics by exploiting the lepton monitoring. We developed the model by using the observable templates, implementing it in the RUFIT software framework. We use the multi-universe method to propagate the hadron production uncertainties on the observables and on the neutrino flux. And we validated this model by exploiting a toy hadron production, model. And so the next steps are to develop a real model for NUBET. So basically this means that we will obtain the templates for the leptons from our Gen4 simulation of the facility. Then for the hadron production, we will use the real data, the one from SPY experiment are being considered, since they are taken with a primary proton beam at 400 GeV, which is the same as the NUBET facility. And then they explore the phase space, a phase space that is close to the NUBET one. And of course, we are working on building a model for both the electron neutrino and muon neutrino flux. So this is a work that is already in progress. In the near future, also the impact of the beamline parameters will be assessed by following the same procedure. And we already started some preliminary tests by studying the error on one of the dipole magnets. Okay, so this was all. And thanks
So-
for your attention.
Thank you, Antonio. Unfortunately, we are a bit late, so I encourage to put the discussion at the level of Slack for this time, and also so we can move to. Thank you again. We can move to the next speaker, which is Paul Kuibert, that will deal with the calculation of fluxes for NuStorm.
Okay.
Hi.
Hello, Paul.
Okay, I'll share my screen.
Okay.
Is that okay?
Yes. Try to move to the second.
Okay, there you are.
Fine.
Well, I'm
Thanks.
going to review the status of the NuStorm simulation because in order to design a suitable detector and understand the physics reach of NuStorm, we need to know the number and energy of neutrinos, which we're going to get for every proton on target. So the schematic is shown at the top, and obviously we have a proton beam from the SPS. It interacts with the target and produces pions, which go down a transfer line. They go into the NuStorm ring and they decay in the production strait and produce muons. And the muons that are captured circle the ring many times, and as they go around, they decay and produce neutrinos. And the neutrinos head in all directions, but at least some of them head towards the detector and interact in the detector. And if you look at it, the efficiencies for the different stages are such that it's not feasible really to do an end-to-end transfer. So we have to break the problem up into sections and stick them together. Okay, so what we need is actually to put together multiple different programs. For the pion production, we'll need something like Fluker or Mars. Then we obviously need to capture the pions and transfer them to the ring, and that involves a piece of accelerated code such as BDSIM or G4 beamline. And then we'll also need BDSIM and G4 beamline for calculating the orbits of the muons and the capture of the muons from the decay. The actual pion decay, of course, is rather simple. It's just a two-body decay with a single channel. And we've written a piece of code called NuSim, which deals with that. Following the production of the pion, of the muons and their orbit, they decay to produce the neutrinos. And again, this is slightly harder, but again, it's just a simple three-body decay. And effectively, we're just worrying about the single channel. We're not worrying about the electron production at the moment. And finally, we end up with neutrino spectrum, both in energy and angle, and that we allow it to interact with a detector. And for that, we need to model the neutrino interactions, for which you use something like Genie. And then we need to worry about how that is seen by a suitable detector, for which we'll use Yang 4. So we link all those together using the NuSim framework. So the way we operate is because we can't, if you like, follow the path of a single particle through from start to finish. We take a parameterized pion distribution, which come from the accelerator design software, and that we use to produce a pion distribution. We decay those pions into muons in the decay strait, and the muons produced are then captured and rotated around the ring. And that provides us with a distribution of muons, which is the distribution which we'll use to create the neutrinos. those neutrinos are simply decayed, those muons are simply decayed into neutrinos, and we propagate the neutrinos to our detector. And that produces a flux file, which is a list of neutrinos with their energies, their positions, and their angles. And that can be used for an input to Gini, which will simulate a suitable distribution of neutrino type events, and they can subsequently be put into GEO4, which will allow us both to design a suitable detector and to determine the physics reach of the experiment. So that's what we're going to do. It's not where we are at the moment. The current status is that the pion production we're getting from NUMI data. The pion distribution from the TARP is given by the target new storm performance, which is the sort of thing which Yaroslav has provided. And as he said, detailed modeling is being done to improve that, but at the moment we're using what you might call a toy distribution. The muon production distributions we get from NuSim. The ring capture we're taking from a paper which is a couple of years old about a new storm decay ring design, which actually uses the accelerator software, but it is not, it's not specific to this incarnation of new storm. And then we use those muons to produce a neutrino distribution, and we propagate that to the detector plane. Okay, so if we see where we're at, the number of useful pions is about 0.1 per proton over the required energy range. And that we got from the NUMI data. And we are just starting to look at studies specifically for this particular incarnation of new storm. There are numbers from older studies from the Fermilab machine, but that's where we are with the machine to be sited at CERN. If we then look at a suitable pion parameterization, we see that what we're expecting is an energy which is about plus or minus 10% parabolically around a central momentum. So that's the energy spectrum we're looking at. And then we're looking at a distribution in X and Y, the transverse distribution from the beam. In other words, what does the beam look like away from the center? And again, we've just got parabolic distributions which are appropriate. And for the angles, we're again got simple distributions which correspond to an appropriate beam emittance. And if we put all that together, we can then look at what we expect the muon decay spectrum to be. And at the bottom, you can see that given those input parameterizations, we end up with a muon decay spectrum, which is wide, goes up to a kinematic limit, and is pretty much flat. But that, of course, is all the muons produced, and those are produced with a range of angles and indeed positions in the beam pipe. So what we have to do is to ask which ones of those muons will be captured by the new storm ring. And for that, we're using, as I said, these plots from the paper from 2018. And there you can see that the Z in this study is the up and down, and is therefore symmetric, whereas the X is the left and right, and the asymmetry in the distribution is caused by the bending of the beam. So if you do that, then at the bottom you can see that our flat distribution gets chopped into two sections, a high energy section and a low energy section. The high energy section corresponds to the forward going muons from the pion decay, and the smaller energy is from the backward going muons. So if we look at that, we obviously can't take both the forward going muons and the backward going muons with the same magnetic field. So the ring will be tuned for the different input energies to pick up the forward going muons. And if you look at that, then you see that what we're predicting from this is a distribution. If we put in a parabolic fit to guide the eye, you can see the parabolic fit is not too bad. Actually, there seems to be some Gaussian mixed into there, which explains why it's both a little bit higher and it goes out a little bit wider. But it does show us that the idea of a parabolic energy distribution for not only the pions but the muons is an acceptable way of looking at the system at the moment. So if we do this, then we can see what the production efficiency is for producing pions around the set of energies that we're expecting to use in this form. And you can see those numbers are a few percent. They vary by actually a factor in between the lowest energy and the highest energy. And all you're really seeing there is as the energy increases, the relativistic beaming tends to push the muon into the acceptance of the ring. And so higher energy muons are pions are more likely to produce muons which are captured by the ring. Okay, so then we take a parameterized spectrum. At the moment, we haven't actually tried to get a parameterization based on the pion decay. Parameterization we're using is a parabolic muon distribution, which is obviously supported by what we can see so far. I think we won't try and improve the muon energy distributions until we have at least some idea of what the simulation from the accelerator modeling gives us. At that point, we'll return to this part of the simulation and produce more accurate distributions. But I think we can see that at the moment, we're certainly modeling what we're expecting well enough. And again, you see the energy looks parabolic. And again, we have a distribution in position and distribution in angles to give us a beam with the appropriate emittance. So we take that muon beam, we allow it to go round the Newstorm ring. The muons decay as they go, and we track the neutrinos produced from their production point and see if they intersect with a detector which we place downstream of the production strait. And then if we look at what the mean muon energy is, and we ask how many of the neutrinos of that energy reach the detector, then you'll find that again, it's changes with energy, maybe not quite as steep a change in energy as we saw before, but again, higher energy means more beaming and better acceptance. And we're going from, say, 5% to about 20%, so maybe a mean of like 10%. So that allows us to now say what the total efficiency is. So at this point, we're getting a total efficiency of about 0.03%. I'm not trying to break them down yet. I don't think that we really have enough confidence in the individual bits to start plotting efficiencies as a function of neutrino energy, but at least we have an idea where we're going. From that, those neutrinos we can create a set of what we call the flux files, and they correspond to the information about the neutrinos as they hit what we've defined as the detector plane. And that is a plane which is 50 meters downstream of the production strait, and its origin, it's 0, 0, and the transverse plane is on the axis of the production strait. And we actually have some of those flux files, and they are being used to generate neutrino interactions in Gini. And we've just started looking at the final state kinematic distributions. And we're going to use those to guide our studies on the physics and the detector design. If I just show you what you see if you see like that. So here you've actually got a plot of a neutrino rate. And this is, as I say, the number of neutrinos which intersect that plane, but it's that plane with a 5 meter by 5 meter cut around the 0, 0 point. In other words, modeling a 5 meter by 5 meter detector sitting at that point. And we obviously look at that with different muon energies. So if you look on the left, there's a muon energy where the mean energy is about 1 JeV, and you can see the neutrino energy goes up, comes down, and is cut off at 1 JeV. If you look at the highest data set we have, where the mean energy is 5.5, then you get a much broader distribution, and it runs out more smoothly and at obviously a much higher energy. Now, those are not in any real sense normalized. What they assume is the same number of circulating muons in the new storm ring. But of course, as I've shown, the number of muons circulating per incident proton depends dramatically actually on the mean energy. So those can be, if you like, internally they're consistent, and between them, it's interesting to look at the heights, but you need to worry about what is the efficiency to get to that stage before we can really make detailed predictions. I do think it is interesting if you look at that clearly you can see there are more events at high energy, which is what you'd expect from the efficiencies I presented. But that actually, if you look, if you take an energy like half a JeV, you're getting about 300 neutrinos in the bin size at 1 JeV, as opposed to about 140, 150 from the higher energy distributions. Now, the question is that factor of 2, how does that play off against the fact that the higher energy distribution is more efficient? So it's not clear at the moment, I think, which is the best way to get half JeV neutrinos. But of course, there are other questions in the sense that if you know that there are no neutrinos above 1 JeV, that can inform the way you do the analysis. So we're still at an early stage in deciding how to separate the running at different beam energies in order to optimize physics that we want to look at. And of course, that gets even more complicated if you add to the fact that higher energy neutrinos are more likely to interact. So here you've got on the left-hand side, you've got the distribution of neutrino energies for a mean muon energy of 5.5 JeV. Where on the right, you can say, well, what happens if we try and fold in the neutrino cross-section. Now that's not a detailed application of the neutrino cross-section. It's just saying, well, the neutrino cross-section goes linearly with energy. So if we weight the distribution on the left with the energy in that bin, what do we get? And you can see, unsurprisingly, it's skewed over to the higher energy side. And again, the studies will need to ask ourselves the question, how many, not only what's the event of neutrinos, but what's the event of the rate of neutrino interactions? Okay, so in summary, for the pion production, we'll look at Fluker and Mars, and that's in the planning stage. For the pion capture and transfer, there's the accelerator code, and as Yaroslav said, the first iteration of that anyway is nearing completion. The pion decay to produce the muons is complete. The muon orbit capture and propagation using the accelerator code is in progress. The neutrino production is complete, and the interaction, we do have some preliminary distributions in Gini based on the neutrino fluxes that have been produced. There is a wiki which contains the information on the project status, and all the data sets which I've talked about are also available. The ones I've talked about are shown here. There are other ones, and there is a description file which tells you what the generating conditions were for the different flux files. Anybody who's interested is free to use it, but please acknowledge the source. And I think that's me.
Okay, thank you, Paul. So we are a bit too late, so I think that unfortunately Rui could not connect live because due to some constraints, so he prepared a recording of his intervention. So it's about the possible sighting of an Inuit and Nustorm at the Muon Collider preparatory facility. So I propose that everyone could look at individually. Otherwise, we will just overlap with the session, which is about to start in 5 minutes. I apologize for this. Anyway, we will have occasion to discuss this in the summary talk and also in the roundtable on Saturday. And also through the Slack channel, of course. So maybe we can profit over the very few minutes if there are urgent questions. Okay, it doesn't seem so. So I think it was a very interesting session, and I would like to thank all the speakers and people who asked questions. So let's make also an applause, which we didn't do before. All the speakers. So thank you, and have a good lunch for people that are on our time zone.
Bye-bye.
Bye.